I'm glad to introduce the last plenary speaker of today, Heather Lee from University of Washington, who will speak about global homological mirror symmetry for genus 2 curves. Heather, you can start.
Thank you. Yeah, hi. I want to thank the organizers for putting together this wonderful conference, and thanks everybody for attending my talk. So this is a joint work in progress with Hani Azam, Catherine Canizo, and Chichu Melissa Liu. It's a little follow-up project to Catherine's thesis. So for the most part of this talk is a lot like a talk for her thesis. So we want to talk about homological mirror symmetry for genus 2 curves. Before we get to that, let's first talk a bit about genus 1 curves, which are 2 tori. So by curve, I mean a complex curve, so a real surface. There are 2 reasons I want to first introduce this genus 1 case. Before moving on to genus 2, one is that this is simpler, so it serves as a nice introduction to homological mirror symmetry. The other reason is that later we are going to view genus 2 curves as hypersurfaces embedded in 4 real dimensional tori. And mirror symmetry for these 4 tori will play a role in the mirror symmetry for the genus 2 curves inside it. And the mirror symmetry story for the 4 tori and 2 tori are kind of similar. So later when I start talking about the 4 tori, you can keep this 2 tori picture in mind to get the intuition for that. So now this example of a torus, on the complex geometry side, any torus is C quotiented by a lattice. Yeah, so for some modular parameter tau, and tau is a complex number in the upper half plane. So mirror symmetry is a duality between complex geometry and symplectic geometry. In this case, the mirror to this torus is also a torus. In general, the mirror doesn't always have to look like itself. So the mirror here is a symplectic real torus with this complexified symplectic form. So, so this tau is a complex number. This omega drd theta is what we would normally call a symplectic form. And this b drd theta is called the B field, is any closed to form. So Polish-Truk-Zaslow proved a homological mirror symmetry result that the derived category of coherent sheaves on this complex torus is equivalent to the Fukaya category on this symplectic torus. So this line here has some very big words. I wanted to write down this statement, but I don't expect people to know what they are. I'll show some pictures to give you an idea. So I can't explain this better than Denis Roux, so I took this picture that he always draws when he talks about this example. So here we are looking at the Fukaya category of this symplectic torus. The point of this category is to study Lagrangian submanifolds and their intersections. So here I'm drawing a torus as this black square with the opposite sides identified. So, so this is a torus. This is a 1x1 square. It's actually scaled, so the total area is tau. So there are 3 lines in this picture. There's this green horizontal line labeled L0. There's this red line of slope -1 labeled L1, and there's this blue vertical line labeled Lx tau, which is defined so the distance here is x. So these 3 lines are 2 circles on the torus. So there are 3 Lagrangian submanifolds on the torus. So the objects of the Fukaya category are Lagrangian submanifolds. And given any 2 objects, the morphism in the category between these two objects is a vector space generated by their intersection points. So here S is the intersection point between L0 and L1, and then between L1 and Lx tau, we have E1, and between L0 and Lx tau, we have E0. So there are also these product structures on these vector spaces generated by these intersection points. And these product structures are defined by the count of pseudo-holomorphic disks, which in this case are triangles that are bounded by these three Lagrangians. So if we want to, so here is this triangle that this three Lagrangians bounds. So we can multiply the intersection points in a counterclockwise order around this triangle. So we have a product of S and E1. So the product of S and E1 is going to be an element in the vector space generated by the third corner, the E0. So S times E1 is going to be a multiple of E0. And what this multiple is a count of all the triangles bounded by these three Lagrangians with these three intersection points, weighted by the area of this triangle. So actually also weighted by the holonomy of a flat connection around the boundary of the triangle, but I'm going to ignore that here for the sake of time. So let's count all the triangles with these boundary conditions. So here we have one. This is a triangle of side length x. So the area of this triangle is x squared over 2 in this 1 by 1 square. But remember, it needs to be scaled by tau. So the area is tau times x squared over 2. And this is not the only triangle with these three boundaries. There are bigger and bigger triangles that wrap around the torus. So they are easier to see in the universal cover of the torus. So here I've drawn the universal cover of the torus. Actually, I've only drawn 4 copies of the square. So here you can see that this orange triangle is the triangle that we had before up there. This pink triangle is a bigger one that wrap one time around the torus, but still have those 3 Lagrangian boundaries. And this bigger pink triangle has area tau times x plus 1 squared over 2. And then there are bigger and bigger versions of these pink ones that have areas tau times x plus n squared over 2 for any positive n. And then there are also these other triangles on the opposite sides with the side length 1 minus x. So this triangle has area tau times 1 minus x squared over 2 or x minus 1 squared over 2. And then there are bigger and bigger versions of this that have areas tau times x minus n squared over 2. So overall, for any integer n, positive or negative, there's a triangle with area tau times x plus n squared over 2. So so in this, so we've counted all these triangles and computed their areas, and we see that now the s times x1 is this number times E0. So so this whole story is in the Fukaya category of the symplectic torus. And this is supposed to be equivalent to the derived category of coherent sheaves. And so this equivalence is going to tell us that Lagrangian submanifolds in here correspond to line bundles and skyscraper sheaves in here. So our three Lagrangians turns out actually corresponds to the structure sheaf. The L0 corresponds to the structure sheaf. L1 corresponds to the degree 1 line bundle on the elliptic curve. And this Lx tau corresponds to a skyscraper sheaf at the point x tau. To justify this, we can look at these three sheaves and compute the morphisms between them. So from here to here, there's a one-dimensional space of holomorphic sections of the degree 1 line bundle. And for each section, there is one map to the skyscraper sheaf tau at O at tau x, given by the evaluation map at this point tau x. So the composition is the evaluation of the section at this point tau x. Up to scaling, this is the Riemann theta function. So which you can see if you look at the Riemann theta function up to this factor, it looks like this, which actually matches with this factor here from the computation in the chi category. So so this justifies like this identification between Lagrangians and the line bundles and skyscraper sheaves. So in this mirror symmetry dictionary, you can look at more Lagrangians and coherent sheaves and figure out that actually any degree J line bundle corresponds to Lagrangians of slope minus J, and skyscraper sheaves corresponds to Lagrangians that are vertical, like this L x tau here. Okay. So, so this is an example of homological mirror symmetry for the torus. So there's always going to be this mirror correspondence between symplectic manifold and complex manifolds, and between Lagrangian submanifolds in the symplectic manifold and coherent sheaves like the line bundles and skyscraper sheaves on the complex manifold. So that's this example. And now let's move on to the complex genus 2 curve. So the complex genus 2 curve is labeled by a modular parameter tau. And this tau is in the genus 2 upper Siegel upper half space. So tau is a symmetric complex valued 2x2 matrix with the imaginary part being positive definite. So we can view this genus 2 curve, theta tau, as a hypersurface defined by the Riemann theta function inside a abelian variety, V tau. And this V tau is a quotient of C star 2 by this group tau times Z2. The coordinates on the C star 2 are x1, x2. So this formula defines a hypersurface inside here. So with the S1, x2 in here. So any element of this group, tau times Z2, is of the form tau times n. So which is this matrix tau times a integral valued 2 vector n1, n2. So when we multiply it out, we get this acting on x1 and x2, and it acts on this in this way, where we exponentiate these two factors and then multiply x1 and x2. So this is a group action on C star 2, and the quotient of that gives us this abelian variety that this genus 2 curve sits inside. So this is actually a 4 torus, this V tau. To clearly see that this is a 4 torus, notice that this space is isomorphic to C2 quotiented by a lattice. And this identification between these two spaces is via the exponential map, where you exponentiate V1, V2 to get X1, X2. So the point here is that for each tau, we get a genus 2 curve sitting inside as a hypersurface embedded in a 4 torus. So there is a SYZ mirror symmetry philosophy due to Strominger-Yau-Zaslow that a mere pair of manifolds emit fiber-wise dual Lagrangian fibrations. So this could work to explain mirror symmetry for genus 1 curves with dual circle fibrations, but it doesn't quite work on genus 2 curves because a genus 2 curve doesn't emit a Lagrangian torus fibration, which in this case is a circle fibration. So because you can see here, like we can have a circle fibration here, here, but then you can't, we won't be able to extend it all the way throughout the middle here. So this is due to the fact that a genus 2 curve is not Calabi-Yau, is general type. So in order to use this SYZ philosophy to construct the mirror to a genus 2 curve, we need to fatten it up somehow. And we do that by replacing this genus 2 curve by a complex 3-dimensional manifold X tau. And this X tau does admit a Lagrangian torus fibration, a T3 fibration. So this X tau is the blow up of V times C along the genus 2 curve theta times cross 0. So why is this a good replacement? I feel like I don't have time to talk about that, so let's just take that. And so we replace the genus 2 curve by this, and then Abuzayed Aru-Kazakov in 2012 actually worked out the SYZ version of the mirror symmetry story for this space. And the mirror to X tau is actually a whole symplectic fibration, Y to C. So this whole symplectic fibration is called the Landau-Ginzburg model. So the total space of this fibration Y is a 3-dimensional complex manifold, and the generic fibers of these fibrations are V check. So this V check is actually a 4 torus, but it's not, it's related to this V. So V check is actually the mirror to V. So remember we talked about mirror symmetry for the 2 tori. So here we have mirror symmetry for the 4 tori that works kind of similarly. So V check is a mirror to V. And those are the generic fibers of this fibration. And the singular fiber is above the point 0. And the singular fiber is a blow up of CP2 at 3 points, quotiented by this group, imaginary part of tau times Z2. So here I'm drawing the moment polytope of the singular fiber. So the critical locus of the singular fiber are these 3p1s. There are 3p1s that are given by the 3 edges of this hexagon. So the hexagon has the opposite edges identified. So there are just 3 edges. So the mirror is this whole fibration like this. But the total space of this vibration is actually 2 complex dimensions higher than the genus 2 curve. So it's pretty crazy, but it's the same dimension as this replacement. So, but if you look at the critical locus of this vibration, the critical locus looks like this. It's actually 1 complex dimensional, and it does look like a bit like a genus 2 curve that's singular and degenerated. If you like, there are these degenerated points. So if you are willing to study the symplectic geometry of this singular thing, then we can take this singular thing to be the mirror of the genus 2 curve. But otherwise, we have to use this whole vibration here. So, oops. So speaking of homological mirror symmetry, Fukaya has shown a general homological mirror symmetry result for abelian varieties that takes care of this equivalence between the derived Fukaya category of coherent sheaves on V and the Fukaya category on the V-check, the mirror. Catherine Canezzo's thesis showed this equivalence between the genus 2 curve and the Fukaya category, Fukaya saddle category of this mirror Landau-Ginzburg model. And she also showed this whole diagram is commutative. So let's talk a bit about this diagram. So here we have the genus 2 curve is sitting inside this abelian variety, this 4 torus. And so any lamp bundle on V can be mapped to a lamp bundle on the genus 2 curve just by restricting this lamp bundle to theta. Okay. So that's this map. And now we can talk a bit about this map here. So given a Lagrangian submanifold in this 4 torus, we want to get a Lagrangian submanifold in Y. So how do we do that? We can take a Lagrangian submanifold in this fiber V-check, because V-check is in the fiber of this vibration. So we can take a Lagrangian submanifold in this fiber and parallel transport it in this fiber above -1, and parallel transport this Lagrangian around a U-shaped curve in the base to get a Lagrangian in Y. So take a Lagrangian here in this fiber above -1, and then parallel transport that Lagrangian to swipe out the bigger Lagrangian in Y. So this is a U map that, that maps Lagrangian here to Lagrangians in Y. And you can think of this U as an infinite circle in the base. That's why we're doing it. And remember that we want to establish a mirror symmetry dictionary between Lagrangians in this 4 torus. We want to establish a mirror symmetry dictionary between Lagrangians here and lamp bundles here. So what Catherine showed is that if you take Lagrangians in this 4 torus, if you take Lagrangians in this 4 torus, that is the analog of this horizontal ones here. You can think of 4 torus like as the 2 tori, like get the intuition. So if you take Lagrangians in the 4 tori, that's the analog of this horizontal ones, and parallel transport it around the U-shaped curve to get a Lagrangian in here, then that Lagrangian corresponds to the structure sheaf on the genus 2. And also, if you take a Lagrangian that's an analog of this slope -1 Lagrangian L1, and then parallel transport it around the U to get the Lagrangian in here, then that corresponds to a degree 1 lamp bundle in here. So earlier, we also talked about how this vector spaces generated by the intersection points. These are the Floor cohomology complexes, and computing the differentials on the Floor cohomology complexes in this case ends up involving counting pseudo-holomorphic spheres. And that count gives a formula that looks like the theta function, this theta function somehow. So Catherine Cesis did this for a particular one parameter family of tau. So in our joint project here, we are doing it for all tau in the Siegel upper half space, the 2x2 matrices. So upgrading her thesis to all tau is mostly immediate, although we are spending quite a bit of effort trying to see that her calculations work for toric Kähler structures that we put on this Y for general tau. So mirror symmetry gives this correspondence between the complex modular space parametrized by this tau on the genus 2 curve and the Kähler modular space on the mirror. And if we work out this construction from here to here, we'll see that this tau actually determines the symplectic areas of these three P1s. So in Catherine's thesis, her tau corresponds to all three areas being 1. So, but as we vary tau, we know that the Kähler parameter on the mirror can't stay in the same Kähler cone because this Siegel upper half space is not a cone. So the Kähler moduli space can be obtained by gluing together several charts. As we vary tau, we can see this transition between charts happening to the sizes of these P1s. For example, there's the Atiyah flop where one P1 shrinks to 0 and then pops up in another direction. In terms of the count of the pseudo-holomorphic